Consider the following problem. So we already started talking about this problem in our first video, and I provided a solution with a casework. Now in this second solution, I will be providing yet two new solutions. One direct count using Burnside lemma, and I would like to thank Rahul Rao, who in his comment suggested that I can use Burnside lemma directly, which actually is correct, so it works out actually. And the second solution is Polya theorem, or Polya's theorem, using the pattern inventory, the cycle index of the group of symmetries, and ultimately the pattern inventory related to that. So let's go ahead and start. So let's first solve this problem, remember this problem, and then let's solve it directly using Burnside lemma in our first solution. So I have solution 1 first. Solution 1. This is a direct count of Burnside lemma. So we have, just to remember the problem, we have a 3x3 square grid, just like in this picture. How many different coloring patterns are there? With 2 red, 3 white, 2 red, 3 white, and 4 blue squares here. And when we say patterns, they are essentially different colorings, in the sense that if you can obtain a coloring by a simple rotation or a reflection of another coloring, then those two colorings are essentially the same colorings, right? So we want colorings that are in a sense different up to rotation and reflection. So if we use Burnside lemma, again the number of patterns, if you will, or colorings you might say, patterns, is equal to 1 over the group symmetries. Here that would be 8. And now we will go ahead and use Burnside lemma, in the sense that we need to calculate the fix of each of the 8 symmetry group elements. Just to remind you, we have the identity, the 90-degree rotation, 180-degree rotation, 270-degree rotation, 4 rotations, and 4 reflections. We have the horizontal, an axis of symmetry which is horizontal, vertical, diagonal like this, or diagonal like that. All right, so we start by finding the fix of the identity. How many of the colorings will remain unchanged if we were to apply the identity, so basically do nothing operation, symmetry on this square? Well, all the colorings will remain unchanged. So, and in total we have 9 factorial over 2 factorial times 3 factorial times 4 factorial. Alternatively, you can write this as 9 choose 2 ways to choose where to place the 2 reds, 7 squares left, 7 choose 3 ways to place the whites, and then the remaining squares will be given to the blue squares. So that's the fix of the identity plus. Now, how many of the colorings will remain unchanged if I were to apply a 90-degree, say, clockwise rotation? So after a 90-degree clockwise rotation, this square will be going to here, that square will go there, this square will go here, and then that square will go back there. So those 4 squares better be the same color. Similarly, this square will be mapped to here, that one there, and this one over here. Again, those 4 squares better be the same color, and then this one can be anything. Well, first of all, because it is the white which has an odd number, the other 2 are even number of colors. So the center square better be white under this rotation. But then, even that is not enough. Why? Because we have 2 reds, 2 whites, and 4 blacks or blues left. And remember earlier that we said that we should have 4 of one color and 4 of another color, which is not the case here. We have enough blues, but we have 2 red and 2 white. That's not going to happen. So this is a 0. Interestingly, 270 degrees will also give you a 0. But first, let's go in order. So let's now check the 180 degree rotation. So what would be the fix of a 180 degree rotation? So if this is an A, this better be an A, and this is an A, that would better be an A. Similarly, this is a B, that should be a B after a 180 degree rotation, if the coloring should remain unchanged to an outsider. If this is a D, that's a D, and finally this is an E. So again, because white is odd, so that E at the center better be white color. Now we have a situation which is doable. Why? Because we have 4 pairs of colors, 2 A's, 2 B's, 2 C's, and 2 D's. And indeed we have we have 2 reds, 2 whites, and 4 blues left. So for those 4 pairs, again, so we have A's, B's, C's, and D's. We need to choose 2 of them to be blue. 2 pairs should be blue because in total we have 4. So 4 choose 2 of them will be blue. And then from among the remaining 2 choose 1 will be red and 2 choose 1 will be white. Or if you will, 4 factorial, if you want to be consistent, 4 factorial divided by 2 factorial, 1 factorial, 1 factorial. We already described that the 270 degree rotation, that one is a 0. And lastly, we need to check the fix of the reflection across the horizontal axis, the vertical axis, and then the 2 diagonals. The 2 horizontal axes, they are very symmetrical cases, so they will be the same result. So I will just multiply as well the result by 2, right? So 2 times. All right, so the horizontal symmetry axis is horizontal, so whatever this color is, that one should be the same color. Same here and same here. This can be anything, anything, anything. Here in this case, well, in this, when we calculate the fix of the reflection across the horizontal axis, we have 2 subcases. Again, because we have 3 whites, like the whites are an odd number of colors, and clearly A's are in doubles, B doubles, C doubles. So the 3 whites, either this horizontal, the second row is all white, or in the second row I have a single white. Does that make sense? So those 2 subcases, let me open a parenthesis here. The times 2 is for the horizontal versus vertical rotation, reflection, I should say. So they are, so it's symmetric, so it's 2 times. All right, so the second row is all white, meaning we have 3 pairs, 2 double A, double B, and double C, and we have 1 pair of red and 2 pairs of blues, right? So that would be just 3 choose 2 ways to choose which of the A's or B's or C's will be blue, and then the remaining one will be a pair of red, right? So that would be 3 choose 2 or 3 choose 1, doesn't matter. Or in the second row here we have a single white, and there's 3 choose 1 way I can decide which one is a white. And then the remaining we have a double A, double B, double C, and like we said, so one of them is white. So suppose that the middle, or let's say the first one is white, for instance. We have 3 choices. It can be either here, the center, or over there. Doesn't matter. And because of the way we have like 2 red, 2 white, and 4 blue left, so these 2 are DD. So again, we have 4 pairs, and that we need to fill, and we have 2 red, 2 white, and 4 blue left. And then, because we are in the case where we have 1 white here, so which we have chosen as 3 choose 1, so we know for sure that these other 2 are non-white. So as a result, one of these A's, B's, or C's will be white again. So 3 ways I can choose which one will be white. And then once I choose, let's say, A's, for instance, or B's, doesn't matter, then we will have 3 pairs of letters left. The A's, the C's, and the D's. For instance, if we go with choosing the white as B's as the white one. So, and then that would be a 3 choose 2 there again. 3 choose 2 ways to choose the 2 blue pairs, for instance. And finally, 2 times the diagonal, right? And let me actually do the picture over here. So we can just pick one of the diagonals. Let's pick the one here, the diagonal axis of symmetry. So whatever color, well, this one can be anything. These 2 has got to be the same. Those 2 are the same. This one can be anything. Those 2 have got to be the same, and this one can be anything. Again, on that diagonal where A, D, and F colors are, I can either have a single white or 3 whites at the same time, because the others are in pairs. So if it's all 3 are white, then again 3 choose 2 ways to decide which 2 pairs will be blue and which one, the remaining one, will be red. Or on that main diagonal, I have a single white, which I can choose it in 3 choose 1 way, meaning the other 2 would have to be a different color than white. So meaning either the B pair, the C pair, or the E pair will be white, which I can choose it again in 3 choose 1 way. And then for the remaining, I can think of for instance, if without loss of generality, if this one was a white, for the D and the F, they have to be the same color now, right? So this is really like a DD. So we decided that I don't know, one of the pairs, off color pairs, is WW here, just because of that. And we have 3 left, 3 choose 2 ways to choose the blue one, and that's it. And I can close this parenthesis as well. Let's do it. And sure enough, that gives us 174 as well. Now the interesting theorem, the solution is due to Polya, solution 2, and that is Polya theorem, or Polya's theorem. It's a very powerful theorem, which really turns the counting problem more into an algebra problem. But before we can do that, I will introduce something different than what we did earlier with Burnside. The idea is to count the length of the cycles. All right, so for all 8 symmetries of the square. All right, so just to remind you, the symmetries of the squares were identity. We had the 90-degree rotation, the 180-degree rotation, the 270-degree rotation, then the reflections across the horizontal axis, let's call it H, the reflection across the vertical axis, and then the 2 diagonals. I'll call them R and S, the remaining 2 diagonals, like that and like that. This one is a vertical axis of symmetry, this one is a horizontal. Awesome, so now let's try to construct the, well, first let's look at the types of the cycles that is being created out of this whole thing, and then we can, well, the identity will construct 9 cycles, each one of length 1. So we can represent this as x sub 1 raised to the power 9, because x sub 1, a cycle of length 1, we have 9 of them. So a 90-degree rotation inside a square, what does it do? For instance, in our example, well, the 90-degree rotation, so this one better be the same as this. So we have a cycle of length 4. Then we have these 4 has got to be the same length. Another cycle of length 4. And then at the center we have a cycle of length 1. Do you guys agree? So we have one cycle of length 1, x sub 1, and then 2 cycles of length 4 each. Does that make sense? So next is the 180-degree rotation. Just to remember it again. So the 180-degree rotation will take this one over here. That guy will be mapped over there. These are all cycles of length 2. This one will map to here. I don't know, I can make it as minus sign. This one will go there, and then finally plus sign. That one is a cycle of length 1. So we have 4 cycles of length 2 and then a single cycle of length 1. So that would be x sub 1, x sub 2 to the 4 power, 4 cycles of length 2. Now 270 degrees is extremely similar to the 90 degrees. It's a minus 90 degree rotation. So as a result, this will be the same, like the 90 degrees. So those two should match. Now the horizontal, an axis of symmetry around the horizontal axis. So we have this axis of symmetry. Well, these two should be the same. That is the same as this one. This one is the same as that. These can be anything. That can be anything. And then this is anything. So really we have 3 cycles of length 2 and 3 cycles of length 1. X sub 1 cubed, x sub 2 cubed. 3 cycles of length 2 and so on. And this one is the same basically because it is symmetric in a sense. And now finally the diagonals. Again, let's draw the shape. Well, these 3 can be anything. And now these opposite ones, they better be the same. So minuses here, triangle here, triangle here. And lastly, let's say plus here, plus here. So we have again 3 cycles of length 2 and 3 cycles of length 1. And length 2 and length 1. And the same here as well for the other diagonal. All right, so once we have these symmetries, we understand the cycles in terms of their lengths. Now we can in a sense rewrite the orbit formula. We call this the cycle index. Let's do it. The cycle index of our group of symmetry. Let's have a look at that. It's 1 over 8 and it will come out something like this. This is the term where we used to put the fix of the identity symmetry, and then we have what? We have this one is unique. Do you guys see that? If you guys want, we can put that one first. We have, well, all 4 of these, they look exactly alike. And then these 2, they look alike. Do you guys see that? So we have 4 of x1 cubed, x2 cubed, and then 2 x1, x4 square. There you go. And lastly now, the pattern inventory. It's a little bit like, so you guys would need to practice this, but the pattern inventory is the following, the algorithm. So we are constructing an algorithm here. Step 1, identify the cycles and the lengths. Step 2, the cycle index. And step 3, finally, the pattern inventory. So for the pattern inventory, all you need is to replace any cycle of length 1, like x1 for instance. You should replace it with the color choices. And in our example, the color choices that we have are, well, they were, they were 2 red, 3 white, and 4 black. So we have red, white, and black basically. We are not concerned about the quantities yet, right? So x1 should be replaced with red, white, and black, or blue, I should say. Wherever you see x2, cycles of length 2, those should be replaced with r square, w square, black square, and cycles of length 3, which we have quite a few. Wait a second. Well, we have no cycle of length 3, so, well, yeah. But if there was, okay, so let me write it anyways. We would have replaced it with this. And then finally, cycles of length 4. Now we have those ones, right? So we have here. They should be replaced with r sub 4, w 4, and then to the power 4. And let's begin. So inside this formula now, we are going to make these substitutions. So let's go ahead and do that. So as a result, the pattern inventory is this one actually. So the pattern inventory, let's move this down here. So these are the related necessary substitutions. All right, there you go. So the pattern inventory would be equal to 1 over 8. And like we said, so there's an x sub 1, a length 1 cycle, 9 of these. So replace it with this one 9 times. R plus W plus B to the power 9 plus. Now this one, we have 1 of length 1, so which is R plus W plus B. And then we have x2, 4 of these ones. R square plus W square plus B square, 4 of these. Plus, let's continue this way, we have 4 times x1 cube and x2 cube. x1 cube, so this one cubed. And then x2 cubed, this one cubed. R squared, W squared, and then B squared cubed. And lastly, we have 2x1 and then x4 squared. 2 times x1 was R plus W plus B, and then what did I say? x4 squared. x4 squared is R to the 4 plus W to the 4 plus B to the 4 square. That's it. So that's the pattern inventory now. So this is the algorithm. Now, in order to finish the count, we need to identify, because we have a certain restriction, right? The restriction that we have is we have 2 red. Let's write that down. 2 red, 3 white, and 4 blue balls, or squares, I should say. Well, really, what we need here in the pattern inventory is the coefficient of the term. So what I need is, what is now the algebra problem that we are addressing now is what is the coefficient of R squared, W cubed, and B to the 4th power. That's what so that will be the answer to the problem at hand. Well, this is now a simple algebra problem, I would say, right? And let's begin. So let me use a different color here. Okay, let's start with the very first. Well, in the end, we shouldn't forget to multiply everything by 1 over 8. I'm multiplying with, yes, 1 over 8. Let's start with this very first term. In total, we have 4 terms. 1, 2, 3, 4. In each term, we need to find what is the coefficient of this term, and then, yeah. So in the first term, R plus W plus B raised to the 9th power. What it would be the coefficient of R squared, W cubed, B to the 4? Well, that's easy, right? So first term, and we have so coefficient at the first term, R plus W plus B to the 9. Well, the desired coefficient will be just a multinomial formula, right? Or if you want, 9 choose 4 times 5 choose 3 times 2 choose 2, or directly it would be 9 factorial divided by 4 factorial, 3 factorial, 2 factorial, and the R squared, W cubed, B to the 4. That would be the coefficient. We don't care about the coefficients of the other terms. Next is the coefficient, coefficient this long term, R plus W plus B times R squared plus W squared plus B squared raised to the 4th power. So now in that expression, I want to calculate again the coefficient of R squared, W cubed, and B to the 4th power. Because from this expression, you can only get even powers of R, W, and B's. So, and because R, W has an odd power here, so it must be that from this term, we have to have a W. We have to choose the W. All right. Now, from the second expression, now that we have taken care of one W, we need an R squared, a W squared, and then a B to the 4th power. And yeah, so that is, I think, straightforward, right? So again, we can simply use the what? Multinomial expression. If you guys want, you can just replace r squared with a u, w squared with a v, and b squared with r UVW, I don't want to call it W, UVZ for it, or XYZ. Okay, let's call it XYZ. If you replace them with XYZ, what we really need is the coefficient of X, Y, Z squared, right? And like I said, this is just a multinomial thing, so which will end up being 4 factorial, 2 factorial, 1 factorial, 1 factorial, with R squared, W cubed, and B to the 4. Yes. Whew, so we are done with that term as well. Now next is the coefficient of, well, that third term, which is 4 times r plus w plus b cubed. I don't want to see that. And r squared plus w squared plus b squared cubed. Now this one we should be slightly careful. Again, from this second expression, we are only going to get even powers. So again, from this expression, we have to choose the term where we will have a single w, but because it's cubic, when you expand it, it will end up having 27 terms. And because well, actually, we have 2 cases here, I think. We can either have we can select either w cubed directly, or we can select a single w and an r square or a w or a b square with it, right? So so if I were to select w cubed from this expression, so let's just do that. Okay, so the 4 is there, right? We have 2 cases. If I'm selecting w cubed here, so what it means is in this expression, I want to select r squared and b to the 4, r squared and b to the 4. Again, I can think of these as x, y, z. So I want a single x and then a z square. And again, this is just 3 factorial divided by 2 factorial and 1 factorial, right? So, okay, the first case is 3 factorial divided by 2 factorial, 1 factorial. I need to decide from which of the 3 terms I select the r square, and then, yeah, that's pretty much it. 3 ways, basically. Okay, plus, or I could have selected a w here, only a single w, and then one of the other 2 terms, right? Either an r square with it or a b square with it. Okay, so how many ways can that happen? So think about it. So we have 3 brackets of r plus w plus b, r plus w plus b, r plus w plus b. Again, so what I'm choosing is, first, once I identify which one will be w, then I need to choose from the other 2 brackets. I need to choose either both of them r or both of them b. So 3 choices for which bracket I will select the w from. And then with the w, I can have a b square next to it or an r square next to it. Does that make sense? So if you guys want, we can do a subcase here. Okay, let's just do a subcase. So how many different ways can we have r square w, right? So 3 ways, basically. 3 ways we can have r square w. And once we have, so this is 3 ways to have r squared w. Yes. And then from the second bracket, we need to select, because r squares are already taken care of, we need to have w squared and b to the 4. Again, this can be done in 3 ways, right? Because we have 3 parentheses. Choose which parentheses you will get the w squared from, and then the other 2 parentheses, you'll get the remaining 2 b squares, right? So b square square. Or we could have done, again, 3 ways. I could have chosen b squared w from the first parenthesis, and then from the second one, what I need is, I still need an r square, a w square, and then a b square. I have 3 parentheses to choose from, right? So think about it. R square W square B square, R square W square B square, R square W square B square. All I need is how many terms of R square, W square, B square. How many ways can that happen? Well, again, this is a simple counting argument. If the first one is R square, then the second one can be W square, the third one can be B square, or the second one can be B square, and the third one can be W square. But this is the case where the first term is R, right? Do you guys agree? So in a sense, I can choose it as R from here, W from here, B from here, or R from here, B from here, W. Hey, this is just 3 factorial, right? Because then I can have W here, R here, B here, and so on. So this is just 3 factorial ways. 3 factorial, unless I messed up. Okay, so hopefully I did not. I don't want to consider the case where I could have messed up. And finally, well, the last case, I think that case is easy. The last case is the very last term. Yeah, so for the last term, we have the coefficient of 2 times R plus W plus B, and R to the 4 plus W to the 4 plus B to the 4 square. Again, from this expansion, all I care is, oh well, I forgot the terms here. The R squared, W cubed, and B to the 4. All we did is just to check, and then dot dot dot. The coefficient of that term, right? The same here, the same here. All right, so the coefficient of, again, R squared, W cubed, and B to the 4. Well, again, from this one, we have to have the W, so 2 times. That one is have to have the W, no doubt about that. So for the remaining, it's an 8 power. Each term will be an 8 power. I want to have a W square, R square, B square term. How many ways can I have a W square, R square, B square? Wait a second. The least W here is a W to the 4. This is 0 ways. There's no way I can get such a thing, right? And now, that's it. That's pretty much it. So we will finally multiply everything, add those 3 terms that we just found, and then divide it by 8. Now what I want is to compare it with what we did earlier. So the first term is 9 factorial, 4 factorial, 3 factorial, 2 factorial. If you check the first solution, I think it seems it works so far. Next is that term here. Let me color it in a different way, blue maybe. You guys see that 4 factorial, 2 factorial, 1 factorial, 1 factorial. If they don't match, I'm going to double check my work. All right, there you go. Now finally, let's have a look at, so therefore all we care is just to calculate the remaining piece, which is, well, the first term here will give us 2 times 3 plus 3 times 3 times 3. And then this term will give us 2 times 3 plus 3 times 3 times 3, right? So, well, inside the parentheses is just 27 here, plus 3 is 30. 30 times 2 is 60, and then we have 60 more here, so 120 here, right? Let's see if that remaining piece, that better be 120. If not, we messed up this count, and I need to do it again. So 4 times, so is this question mark 120? Because this one is just 0, so 4 times, we have 3 to 1, 2, 1, so this is just a 3 plus, and then we have 3 times 3 plus 3 times 3 factorial. Okay, I'm not sure about this. 9 plus 3 factorial. Yeah, that's not gonna work. Okay, so where did I mess up? Or maybe it does. Hold on. Does it work? 9, and then this one is 27 times 3, which is 81. Okay, we are way off. All right, so let me double check my work again. Okay, so how am I way off here? Okay, let's check this. Okay, where did I mess up in this count? Oh my gosh, what am I thinking here? This is a 6. That's not 27. What am I thinking? Yeah, that's a 6. 6 times 3 is 18. Yay! I'm happy again. So this is 27 plus 3 is 30. 30 times 4 is... Yay! Okay, it matches. So Polya's theorem work. Well, right now, because the problem was relatively simple, I mean, it's just a 3 by 3 square. If this was, say, a chemistry problem or a physics problem, you are investigating the symmetries of an atom or a molecule with a bunch of like 200 electrons and protons, and you are looking at the symmetries of those things. Obviously, solution 1 will no longer be a viable solution unless your counting skills are really good. And in those occasions, I mean, the best way would be to go with Polya. I'm yet to use Polya actually in a real life problem. Almost in all the problems, I'm using Burnside lemma, in combination with symmetry, just like the previous video that I posted. But just for completeness sake, I wanted to share with you the statement of Polya's theorem. I'm in no way of proving this theorem. For those of you who are interested in a proof, I'm using an introduction to combinatorics by Alan Slumson. That's the book that I benefited for this presentation, so you guys can refer to that book as well. Awesome. So we're done. Hope to see you guys next video.